What's up, team? This is the geometry similarity review that we did in class November 14th. Feel free to pause, fast forward, skip around, do whatever you need. I'm going to work through each of these problems, and I'm going to try to do it as efficiently, but also explain things as I go. So here we go. Number one, directions for the first four say each pair of figures below is similar. So that's key. They're telling us that it's similar. We're not trying to prove that they're similar. That's coming later on. Right now, they're telling us that they're similar, so we're going to write a statement and solve for x. Remember with the similarity statements that the order of the letters super matters because the corresponding vertices or the corresponding parts all need to be in the same spot in their respective statement. And then solve for x. So we're going to get our algebra on a little bit. Okay, let's just dive into a similarity statement because I feel like the way I just described it was, I don't know, annoying. This first statement, we have this kind of wonky figure here, then we have another wonky figure here. We're told that they're similar. To me, it looks like, well, this one's clearly bigger, but it looks like we took the smaller one and we reflected it and then it grew a little bit. So this one, we could say, I'm noticing we have the letters A, B, C, D, E, and F. So I'm going to start with that. We'll say that A, B, C, D, E, F. That's what we're going to name this figure, A, B, C, D, E, F. But now we need to find the corresponding sides. So if this thing was flipped, I think A would be corresponding with U. But then we're going to go the other direction. So A and U, and then B and Z, and then C and Y. And if we keep going around, it goes X, W, V, and U. Ran out of room, cool. So this says that A, B, C, D, E, F is similar to U, Z, Y, X, W, V, U. Sorry, that's kind of clunky. Okay, so that's the similarity statement, but now we need to solve for X. This is where kind of our algebra piece comes in. So we know that X is over here at WX. So we need to create some sort of statement that involves WX. And we know that all the corresponding sides are proportional. That's important. I'm noticing that WX is right here in the middle of our statement, the fourth and fifth letter. 1, 2, 3, 4, 5. Oops, I don't need that U at the end, huh? How silly. Okay, I went all the way around. Not wrong, just redundant information. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Great, it's all here. 1, 2, 3. 1, 2, 3, 4. Okay, DE. Gosh, long way around. So DE are the fourth and fifth characters in this statement. 1, 2, 3. XW are the fourth and fifth characters. The reason why that's important is because XW and DE must have proportional side lengths. They are corresponding sides in these similar figures. So DE is over here like so. Now we get to pick any other two of these corresponding sides. So I'm going to pick ZU. And ZU is the first two letters, so they are corresponding to AB, which is given here. Okay, so WX over DE must have the same ratio as ZU over AB. WX, that's our unknown, that's our X. DE, given, that's 3. ZU, that's here, that's 10. And AB is here, that's 8. Great. So now if we multiply both sides by 8, we learn that 8x over 3 equals 10. Multiply both sides by 3, 8x equals 30. Divide both sides by 8, and x equals 30 over 8, or 15 over 4. This could also be represented as 3.75. So either of these representations are appropriate. Okay, let's pick up the pace here. That was way too long for the first problem. Here we go. We have R, E, C, T. And then if we just flip this a little bit, it ends up being corresponding to N, G, L, A. N, G, L, A. It's tempting because it looks like it spells rectangle here. Don't fall for that temptation. Okay, because they are rectangles, however, we know that this side has a length of 6, this side has a length of 3, this side has a length of X, and this side has a length of 4. Great. So we can set these up. I'm going to do AL. AL are the last two, so they are compared to CT. CT is 6. Oops, I should show all the work here. CT. And then I can pick really any other side. So I'll do NA NA is first and last, RT is first and last, that's 3. RT, I'm plugging in the values before, I'm getting ahead of myself. So AL is X, CT is 6, NA is 4, and RT is 3. Great, multiply both sides by 6, and we see that X equals 24 over 3. Well, we know that 24 over 3 is 8. So X equals 8 in this case. Pushing on, number 3. We see here that triangle, let's call it SMI, is similar to, well, S is this congruent angle here, so I'm going to match those up, H, and then M goes to C. It's the one that kind of sort of looks like a right angle, but we don't have enough information to say it definitely is, and it goes to R. So triangle SMI is congruent to triangle HCR, just a rotation and a dilation. So setting this one up here, I'm not going to show as much of my work. Hopefully we see that IM has a length of X, and IM is associated with CR, so it's X over 36 equals, now I'm going to do MS, which is 24. MS are the first 2 letters, so HC is 12, like so. Great. So now I'm noticing that this reduces down to 2, so I'm just going to say X over 36 equals 2. Multiplying both sides by 36, and I see that X equals 72. Boom. Number 4. Got this pentagon thing going on here. It looks just like a slight rotation. So we can say that this thing here, so L-A-C-E-Y, L-A-C-E-Y, the name Lacey, and then it's I-T-H-O-M, Ithom. Not sure if there's any special meaning there, but those are the corresponding sides. This is a correct similarity statement that'll work just fine for us. So AL is going to be our unknown. AL is the first 2 letters, so IT over here is important. It's going to be our 11. And then I can pick any other 2 corresponding sides. I'm going to pick LY, first and last, because I have IM, first and last as well. So, oh gosh, LY I said, so that's 15, and then IM is 10. Great. This one's going to be a little bit annoying here. I'm going to multiply both sides by 11. So that means X is going to equal, gosh, 15 times 11 in our numerator. I don't know what 15 times 11 is. I'm going to grab my calculator. Sorry for shaking the thing. 15 times 11, that's 165. So I have 165 over 10. So X equals 16.5 if I do that division there. Great. Let's pick up the pace even more here. So determine if each pair of angles is similar. If they're similar, please justify your answer. So this is where we're going to use the side, angle, side, or the angle criterion or theorems here. So this, I'm noticing, if you just kind of lay this down as it were, you'd have the 36-degree angle and the 47. We know the triangle sum theorem demonstrates that all 3 angles must be congruent. So we'd say, yes, these are similar by the angle criterion. That's the one that we studied together. Great. This next one, we have side lengths of 9, 24, and 32. And then we have side lengths of 4.5, 12, and 16. So I'm noticing that these are definitely proportional. So I have 9 over 4.5. That's going to be 2. And then the medium-sized one is 24 over 12. That also has a ratio of 2. And then the large side's 32 over 16. So all of these reduce to 2, all 3 corresponding side lengths. So I'd say, yes, these are also similar by side. Now, note that just because we have the 3 side lengths is not enough information to say that side works. The fact here is that all of them, the ratios are congruent to one another. They all have a ratio of 2 in this case. Nothing special about 2, but the fact that they're the same is quite important. Okay, number 7. We have side lengths of 48 and 12, and then we know nothing about any of the other sides. Okay, interesting. Then we have a 53-degree angle, 55, but over here we have 55 and 72. Remember the triangle sum theorem? Three angles inside must add up to 180. So if I take my calculator, I do 180, and I'm going to subtract 53, and I'm also going to subtract 55. Watch what happens. Boom. That means this angle here must be 72 degrees. I'm noticing that these two angles are the same, and then these two angles are the same. So all of a sudden, we have all three pairs of corresponding angles being congruent. So we'd say, yes, these are similar by angle, angle. It turns out that these side lengths are irrelevant to us figuring this out. It tells us that there's a scale factor of 4, that's nice and neat, but that doesn't actually prove that they are similar. Moving on, number 8. We have a side, an angle, and a side, an angle, and a side. So it makes me feel like it's going to be side, angle, side, but we need to definitely demonstrate that the sides are proportional. The 54s, those are good. Those clearly match. But now we need to show that 45 over 15 is equal to 9 over 3. Hopefully you see pretty quickly 45 over 15 is 3, 9 over 3 is also 3, so it checks out. So we'd say, yes, these are similar because of side, angle, side. Here we go, we have this right triangle. Obviously the right angles match, but looking at this, the hypotenuse, that's the long side, is exactly twice the length. And then here the 8 and the 10, that's just not enough information, because if this was the 16, I'd feel good about it, but it's not. So I'd say not similar. Even though it feels like it should be, it's just not. We don't have enough information. All right, last one on this page anyway. So we have the 46 degree angles, that's great. And then we have 7 and 12, and then 14 and 32. So if we can demonstrate, so if this is true, if 7 over 12 equals 14 over 32, then we definitely have similar triangles here. If this is not true, let's put a question mark here to really demonstrate this. If this is not true, then it's a no-go. So I'm just going to check this using decimal approximations. So I'm going to do 7 over 12. That's 0.58 and 3 repeating. So I'm just going to remember that. 5, 8, 3, 3, 3, 3, 3. Now I'm going to do 14 divided by 32. And if I get the same response, the 0.583333, then we're good. They have the same ratio. If I get anything different, then we're not good. Then these are not similar. Okay, these are not similar because 0.4375 is not the same as 0.58333333. So we'd say not similar. Great, moving on. Same question for 13 through 16, just different examples here. Here I'm noticing, again, a right triangle, those match. And then 7 and 14, well, 7 times 2 is 14, that's pretty quick and easy. The hypotenuse here though, if this was, if it was actually doubled, this would end up being a 26. So we cannot say, I'll write out the work, 14 over 7 is not equal to 39 over 13. So these are also not similar. Similar. Here we go. Nothing's known about the angles, but we have 3 side lengths for both of these. We cannot definitely say side, side, side until we show that all of the sides, the corresponding sides, are proportional. So that means what must be true is, let's see, I'm going to box these corresponding sides. I'm going to circle these ones, and then I'm just going to underline the remaining. So the ratio of these corresponding sides must be the same. So that means 10 over 7, those are the ones circled, must equal 12 over 9, those are the ones that are boxed, and that must also equal 15 over 12. Well, let's see, do we have the same ratio here all the way through? My gut says no, but let's check it out. So I just did 10 divided by 7, I got 1.4 blah, blah, blah. That's this one here. Let's make sure everything matches. 12 divided by 9. 1.333, they already don't match. So this definitely is not going to be a similar triangle. For funsies though, let's go one further. I'm doing the 15 divided by 12, and I got a different ratio altogether. So these are not similar. Again, it's tempting just to say like, oh, I have all 3 sides, so this must be side, side, side. That's just not the case. So the sides must be proportional. Okay. This one here looks like we don't have a whole lot of information. We have a 90 degree angle and a 50 degree angle. Well, I'm noticing we have 2 of the 3 angles and that these angles must add up to 180. So 90 plus 50 plus 40, that is 180. Here we have 90 plus 40 plus 50, that's 180 as well. So all of a sudden, with just that little piece of information, we can see that these are similar because of angle, angle. Now, of course, we have all 3 angles, but the criterion doesn't require all 3. Number 14. We have a side length of 20, 40, 50, and then a side length of 10, 20, 25. Notice how this is not drawn to scale. Clearly, this 20 looks like it's the same size as the 50. Whatever, we're acknowledging the numbers, not the picture so much. Corresponding sides, we have a 50 and a 25. Well, 50 is exactly twice 25. That's cool. 40 is exactly twice of 20, and 20 is exactly twice of 10. I'm not going to show all the work. It's this problem, but with numbers with a pretty clear scale factor of 2. So I'd say, yes, these are similar because of side, side, side. Sneaky one coming your way. There are 2 triangles here. There's the littler one, and then there is the larger one. Notice how there's arrows on these portions here. That means that those sides are parallel to one another. Now with parallel sides, remember corresponding angles must be congruent. That was from our last unit. So these 2 angles here in purple must be congruent to one another. In the same way, these corresponding angles here in this kind of peachy color must also be congruent to one another. So we already have similarity by angle in this case. But for funsies, just to point this out, notice how they both share this top angle as well. It's the same angle for both of them. So we can demonstrate that all 3 angles are indeed similar to one another. So for this one, I would say yes, or just similar because of angle, angle. We don't know anything about side lengths, but we definitely demonstrated the angles are congruent to one another. Okay, here's another one. They're kind of together. We also have these parallel lines. The first thing I'm noticing here is vertical angles. Those must be congruent to one another. I'm also noticing, well, we have parallel lines and a transversal in this case. So we have some alternate interior angles going on. These angles must be similar or congruent, as must these. And that's just alternate interior angles from the last unit. So we demonstrated all 3 sides, only needed 2 of them, similar by angle, angle. Moving on. Decide if each pair is similar. If they're similar, write the correct similarity statement. So it's the same process, but now we're actually using the letters and writing the statement out. So this one's pretty clear cut, 82 and the 82, 16 and the 16. I'm not even gonna look at the last one because I only need 2 of them. I know that they're gonna match because both angles must add up to 180. So I would say triangle, and because there's a letter or a word here, BOX, I'm gonna use it, is similar to triangle NCA. It's tempting to do CAN, but it doesn't work. And then the similarity statement, okay, and how do we know? We'd say by angle, angle. Next one, 2 different triangles here. Let's see, let's kind of make a game plan here. I'm not convinced that these are similar. This one we have 3 side lengths, this one we only have 2. Yeah, so if we did 12 over 15, I just don't think there's a way to make this work. So 15 over 10 would have to have the same ratio as 22.5 over 12, and that's just not the case. So this one's not similar. Not similar as much as we want them to be. Okay, 19, 20, and then the big one, the proof for 21. Number 19, we have corresponding angles that are congruent to 122s. Great. And then we have these corresponding sides, 20 and 15. So if 20 over 15 has the same ratio as 12 over 9, then we're good. Then we'd have side angle side. Let's see if this is true. So 20 over 15, 20 divided by 15, 1.333. I'm just actually going to reduce this as a fraction. I'd rather do that. We know that 5 goes into 20 4 times, 5 goes into 5 3 times. And then here, 3 goes into 12 4 times, 3 goes into 9 3 times. So these both have a ratio of 4/3. So we'd say, yes, these are similar triangles. So the whole statement, we could say triangle, let's do AIL. AIL is similar to triangle MSE because, or by, SAS, or side angle side. This last pair of triangles here, we have a 60-degree angle, 60-degree angle, and then here we have the two angles on either side, or the two side lengths of either side of the 60-degree angle. Here we do not have that. There's a big noticeable omission here. So for this one, we just don't have enough information because we cannot find this side length. So we cannot use side angle side. We only have one angle on the inside, so we cannot use angle angle, and then we don't have all three sides, so we cannot use side side side. So we don't have enough information to call them similar. So you can either say not similar, or you can just say not enough information or something like that. Okay, last one. In the figure at right, we're given that side AB is parallel, that's what the symbol means, to DE. AB, parallel to DE. Is triangle ABC similar to EDC? Use a flowchart, organize, and justify your answer. So I'm gonna do that on a separate piece of paper. Here is my separate piece of paper. We need to make some observations, need to make a game plan, gotta figure things out before we even start flow charting. So the first thing I'm noticing here is that we have some given information that needs to be recorded. So in my flow chart, I'm gonna write down the fact that AB is parallel to DE. This is vital information, and it's given info. So this is going to be the beginning of my flow chart here. I'm going to throw another piece of paper under here to make it easier to write on. Great. Well, what's the major consequence of this? This is a big deal. Otherwise, we wouldn't have written it down. Well, because these two lines are parallel, we can definitely say that alternate interior angles are also parallel to one another. So angle ABC has to be congruent to angle EDC because we have parallel lines with a transversal. In the same way, I'm going to change the color of my pen here to demonstrate that this angle, these two angles must also be congruent for the same exact reason. So let's capture that. So because this is true, and I'm going to focus on the one in red here. So we can say that angle ABC is congruent to angle EDC. And how do we know? Because alternate interior angles are congruent. Kind of full of symbols and notation here, but all good. Okay, sweet. So let's take a step back before we keep flow charting here. This is all true, this is all good, but we need to continue making our game plan. I think I jumped the gun a little bit. We've shown that two angles here are congruent to one another, two corresponding angles, and that really is enough to demonstrate using AA that triangle ABC is similar to triangle EDC. I'm not going to use these angles in green, however. I'm going to use a different move. If you use the angles in green, you'll be just fine. You're correct. But I want to show you something different here, another way to approach this, because I'm noticing that these two triangles, when they butt up against each other, create a relationship known as vertical angles. Vertical angles must be congruent to one another. That is a true fact that we've studied previously. So I'm going to capture that piece of information in my flow chart here. I'm going to say that angle ACB is congruent to angle DCE. Forgot my angle symbol. And why is that true? Because they're vertical angles. Vertical angles. This does not depend on any other prior information. So we don't want this, just because these are parallel does not lead to this information. The reason why this leads to this information is because, well, without this given information, this wouldn't necessarily be true. This is given from the figure, right? So in our knowledge of vertical angles. Okay, our last piece of this plan is we need to put all the pieces together. We're showing that these two triangles are similar by angle angle. We've demonstrated that these two pairs of corresponding angles are congruent. So we're just going to jump to our conclusion. Our conclusion is that triangle ABC is similar to triangle EDC, and we know that because of angle. Now, to complete our flow chart, well, here's one of the pieces of information that we've demonstrated regarding the first pair of angles, and this is the other part of the information that demonstrated the second pair of corresponding angles. So when using angle, you're only going to have two final bubbles or flowchart chunks or whatever that lead to your conclusion. If you're doing side angle side or side, you'd need three different bubbles that lead to it. And here, remember, this is kind of funky. You need this to prove this. You cannot just jump to this fact, alternate interior angles are congruent, because the pushback that the audience would give you, in this case, I'm the audience, and this is the pushback I would give you. I would ask, how do you know that? Alternate interior angles aren't always congruent. There's a necessary factor that goes into this. And then you could respond like, well, these are parallel, therefore this must be true. Yes, great, that's a valid argument. But without the fact that these are parallel being stated, that's just not the case. Okay, hopefully this is helpful. Take what you need, ask me all the questions you have. Best of luck, you got this.